So, welcome to this meeting. I called it originally workshop, but just as I mentioned, it's not really anymore probably going to be a workshop. It's more like a presentation. So those who are watching in YouTube, that's going to be mostly a presentation. Maybe the people who are here in the meeting, they will ask questions. That's fine. My chat is open, so in case you would like to write your question or your comment, do it. You can do it there, or you can open your mic if you like, and if you are okay with the recording and being published, and you can ask it there. My name is Gabor Szabó, as it was advertised earlier. I have been programming for about 40 years now. I wrote for many years. I was writing and teaching Perl. Then for probably even more years, I was teaching Python. Well, it can be less only because it started later. So some years I was teaching Python and working in writing Python code. And the last year I started to also write in Rust, which is a very interesting language. Right, difficult but interesting. And so part of my work is teaching at the corporations. Part is teaching at the Weizmann Institute of Science in Rehovot. And I also go and consult with companies, helping them either improving their programming methodologies, let's say, introducing version control, even in teams where they don't use it, introducing testing. That's one of the areas that I really like. So those people who were here at the previous meeting 2 days ago, they know we were discussing testing, and you can see the video of that one. And I also help introducing continuous integration, and we're going to have a meeting about continuous integration with GitHub and with GitLab as well later on at one point. If that's interesting for you, please follow the group and see if the scheduling is right. In this meeting, we are going to talk about functional programming. Functional programming is, so there are several paradigms of programming, and one of them is functional programming. I actually going to I'm going to share my screen, and on my screen I'm going to put the slides that I use sometimes I use when I'm teaching. So let me share in a second. I'm trying to just click on the right buttons, and hopefully now you're seeing the website, the Meetup website, where you have the advertisement of this meeting. By the way, let me mention that part of the reason that I can give these presentations free of charge is because some people are sponsoring me through these channels, GitHub sponsors and Patreon and PayPal. And if you find these meetings and presentations useful, then please consider doing that as well. So these are the slides on this website. I don't know how well can you see the address bar at the top. It's code-maven.com. I'm going to put it in the chat room. Actually, I don't need this index at the top and the end. This one. Okay, I'm also going to put it in the chat room, and I will put it underneath the video. This is where the slides of all my Python training slides are. There is there a link? No, I'm not sure if there is a link. So let me include this one, slides. This is the place in GitHub where the source of all these slides are. So all the slides are in GitHub. You can clone them. You can get all the examples that I'm going to show. And during this meeting, I'm going to show you quite a few of I'm going to go over the slides of the functional programming part, or at least some of them, and we're going to also edit some of the files. So these are these chapters, and this is the functions chapter, and this is the functional programming in Python chapter. And there are a couple of others, the iterators and generator expressions, which we might be able to cover. We'll see how fast we go. They are sort of related. If we can't cover them now, then we might have a separate meeting for them. So let's talk a little bit about programming paradigms. You are probably familiar with what we call procedural programming, where you write And it's a bit confusing because we are basically writing statement after statement, and we are also creating functions. But this is not the functional programming. So it's called procedural programming. And then another paradigm that we know is the object-oriented paradigm. And in Python, you can also write object-oriented code. And if you have anything relatively complex, you will start to create classes and instances of those classes. So you're going to write object-oriented code. And so both can be done in Python. As opposed to this, there are languages which are primarily or only procedural. So for example, C, as far as I know, you can't write object-oriented. And then there are other languages which are primarily object-oriented. For example, Java. You can't really even print to the screen without creating a class and so on. And then there are languages like declarative languages, for example, SQL, where you basically tell the computer, do something or get me these results, and how it goes by finding those results, that depends on the computer. It's not, or the engine behind it. And then there's the functional programming part, which there are languages which are purely functional, for example, Haskell, and you can't write procedural or object-oriented in those languages. Python allows us actually these three, okay? Maybe even declarative. I'm not that familiar if there's any that kind of thing. Probably there are some playing around with it, but some libraries. But the core Python can allow us either to write procedural. We don't need object-oriented. We don't need anything functional in order to write Python. We can write object-oriented. Obviously, you probably wrote it. And in many cases, that's what is considered advanced. And then there's the functional style. And we are going to see the functional style. And just to cut it short, you might have seen map and filter and reduce or list comprehensions or generator expressions. These are basically the constructs of the functional style programming. Now, I'm not saying that we are going to start writing functional programming in Python. What I'm saying here and what I'm showing here is the functional elements of Python programming. So the functional programming style elements of what Python provides us, both so we can understand, and because many people I encounter definitely during training, but also at companies, they are not really familiar with things. And here are a couple of notes that I'm going to skip now of the advantages of functional programming and why in many languages, functional programming is getting more and more accepted, valued, promoted. I don't know how to call it. There are a couple of things that functional programming helps us avoid various bugs and various issues. But you can go over that. So let's look at the examples, and I'm going to also need a terminal and not the one that I just opened. I have opened. Okay, so here is a terminal. In this folder, and why is it so small? Is it small? No, it's not. I think it's the size is good, right? Let me know if the font size is not that good. So in this folder, we have all the examples from the slides, specifically from the functional chapter. So here in the slides, you will see examples, and above them links. These are actually links to the GitHub, the repository on GitHub, where we have the actual example. So you don't have to copy paste in case you would like to play with something here. So let's start with this, and I'm going to both show the slide and actually switch to the computer, to the terminal, and show it there. So this example is called iterables, and before I do, actually, I need to check if my virtual environment is running. No, so I'm going to start a virtual environment, even though probably I don't really, probably won't need anything from that, but it's better to do it now than later. So I have this example that we saw in the slides called iterables. So let me, iterables.py. And I can go over this. there is what we have here is a list of numbers. And basically what I'm showing in this example is that we know that there are various data structures in Python that we can iterate over them. I don't even really need to do this now. Let me just run the code so you can see the results. If I run the code, you will see that here we go iterate over the elements of that first list. Let me show you the source of this. So here we have the list, and then with the for loop, we iterate over the elements. And that's nothing special. It's nothing functional yet. I'm just showing that this is common thing that we know. And in the same way, we can iterate over the elements of a string. And the elements are the characters. Or you might be familiar with the range function, and we can iterate over the elements of what the range function returns, right? So we call the range function. Usually you don't do this. Usually you put the range function right here, but I'm having a point here. I'm showing something, and that's why I added it to this variable. So I called the range function and assigned it to some variable, and now I'm iterating over it. And the question is basically, what is in this variable called RNG? I enlarge it further. So you can see that in that variable, we have something which is called range 392. Now, people who have used Python in the older days, when Python 2 was still available, might remember that this range function used to return a list of numbers, but not anymore. Python 3 switched that, and range doesn't return the list of values. What it does, it returns what I would call the promise of having the range of numbers. Okay, it basically returns a range object that we can iterate over. So you could see that in this iteration, it produced the result. So we could iterate over the numbers. But if we print out just this RNG, what we get back is just a representation of this in a textual representation. Okay, so what is this? What is this range function? What can it do? You might know, or if not, let's just go over quickly. So the range function can get 3 parameters, and then it will generate the numbers from the first value till the second value with steps given here. So we have 392, meaning starting from 3 with jumps of 2 until we reach 9, but not above it. And if you have only 2 parameters, then the start and the end, and the step defaults to 1. And if you have only 1 parameter, that is maybe surprisingly, it's not the start, as some might think, is the end, and then the start defaults to 0, and the step defaults to 1. Okay, so that's the way range can be used. But in every case, what this call of range returns is the range object. Okay, it's not the list of the values. And we can here as well, we printed out so here, what we have here is the range, call the range function. We are printing out whatever we got. This is the range function, as we saw earlier. We can use this dot, we can use the type and then dot underscore name to get the name of this object. You can do this with any object in Python. So here we can see that the object is called range. And then you can see that I can iterate over the range function. I can iterate over again, but iterate over it again. Yeah, and I can even access a certain element in this range. That's actually a little bit surprising to me at this point, but right. And you can even ask what is the length of the range. But that's what the range object provides. It's not true with all the iterables, actually. Okay, so range doesn't generate the list. It just provides the opportunity of having a list. So why is it good? Why is it valuable? Why not just generate the list and get over with it? And at this point, this is partially because of size. We can save a lot of memory by using this range object. That's part of the reason. We'll see later on also processing time, how we save processing time as well. But for now, it's the space. So here in this example, you can see that I called the range function, received this variable RNG, and then I can use the list function to flatten out the actual list. So you can take any iterable, okay, what we saw earlier, call the list function on it, and then you will get back the individual values from that iterable. Now, in this case, I call the list, and if I print out now RNG, I get back this object, the representation of the range object. But if I print out the numbers that I have here, then I get back actually the actual list that was generated. So this already created the list. Now, yeah, this one is just a different list, okay? That's another list. Doesn't really matter. I'm not sure why I have it here. What is interesting is that there is this function called getSizeOf from the sys module that we imported here that will return us the size of a variable. And as you can see, the range object itself takes up 48 bytes. Fine. The numbers objects takes up 112. Now, in itself, this might disturb you, that why is a list of 3 numbers taking up so much memory? But that's because I think the overhead of having an empty list is already like 50-something bytes, and then each number is also relatively large. And well, Python is not very, it's quite wasteful in memory. Okay, that's part, but it provides us some flexibility, or a lot of flexibility. So that's why it is. But it doesn't really matter why. The reason that we can see is that the range object that represents, in this case, those 3 numbers, or the possibility to get those 3 numbers, is less than half of the full list. Now, if you go to the next example, here, I actually created a little table where I'm going over, basically, I'm going over from 0 till 21, or more correctly, till 20, because this is always Python always excludes the topmost part of a range. And for each one, I call the range object, the range function, to generate this range object. And then I check what is the size of that range object versus the flattened list. So basically, what I'm interested in is if this range generates a list of 0, 1, 2, and so on elements, then how much they differ the range. And as you can see, the range object itself doesn't change its size. Doesn't matter if it represents 1 number or 20 numbers or actually 10,000 numbers. It doesn't matter. It's always just 48 bytes. On the other hand, the list, the size of the list, or the memory footprint of the list grows, obviously, I guess, as the list grows. So you can see that for 20 elements, it's already a substantial difference. Now, imagine a list of 1,000 or 10,000 elements, and you can suddenly see that why flattening a list is very wasteful memory-wise. So that's why using a range is good. And we are getting to the functional part in a bit. So wait a second, I think I skipped over one thing. Okay, so now we know that the range is better because it saves space. Let's see a different example with something else. Here we have a bunch of numbers, a list of numbers, and a very simple and rather stupid function that gets a number and doubles it, just 2 times the number. Now I'm using a really simple function, but the same idea would work with any even complex functions that get one number and returns another number. So the basic thing that I would like to call this function on every element of this list. How do I do it? And generate a new list. The regular thing that people would do without the functional part of Python is creating a new list, an empty list. Okay, we call it double numbers, iterating over all the values in the original list, calculating the result for each one of them, and appending the result with the append method to this new list. Okay, that's what normal people do, or that's what people do who don't know the functional part of Python. This is what you would do in many languages that don't support the functional style programming. It's fine, but this is what you do. This actually means, if I would like to go behind the scene a little bit, that in reality, this operation allocates some space for the double numbers list. And every time we append a value, Python has to decide what to do, has to allocate more memory. And sometimes it's just enlarging the memory, and that's relatively easy. But sometimes Python won't be able to add more values after the current values. So it has to move the whole data structure to some new place. So it also takes time. Obviously, because it's just 4 elements and everything is so small, we don't see it. But this is part of what might cause relative slowness in Python, that keeps moving the data to other places. Now let's see how can we do it better with the map function. The map function in Python, what it does, it receives a function itself. So the first parameter of this map function is a function, and then the rest of the parameters are iterables. So it can have one or more iterables after it. And what the map function does, let's take one, assume that we have only one iterable, and then this function is a simple function that gets only one value and returns one value, like we had in the previous example. So when we call map with double and numbers, what map does is calls the double function for each one of the values in this iterable. So it will call double on 1, and then on 2, and on 3, and on 4, and then it will collect all the results and return them here into these double numbers, all the results. Okay, that's what basically map does. Or is it? Well, what is in these double numbers? If we print it out, this is what it's going to say, probably with a different address in the memory. So this is just an address in the memory. We don't really care about it in our world. So this is an object. This is not the result. This is not the list of numbers doubled. This is just a promise, just as with the range, a promise to have those doubled numbers. And we can indeed iterate over this map object and print out the doubled numbers. Okay, so we had something very similar to, we managed to do something very similar to what we did earlier, but instead of getting instead of getting back the resulting list, we got back the promise of that list. And you can start thinking, if it's the promise of that list, then, so it's not really the list, just an object can represent the possibility of having those values, then it probably doesn't take up so much space. And in a minute, or maybe a few more minutes, we'll also see that it also doesn't do all the processing at this point. It only does the processing, the calculating, the calling of this double function when we actually need the value. So suddenly we also save, or we might save, a lot of processing power with this. So here, what you can see is the same example with the double function, and we call the map, but in this case, we are calling list on the result. Okay, I could have, and let's go back here actually. Let's take the map example. Okay, so what we had here, let me run this, Python map, this is the code, this is the name of the file. This is what we saw in the previous slide, that it says the map object and then the list of values. I could, instead of this, I can do this. D equal list of these double numbers. DBL, let's say, okay? And now, if I print out this DBL, then it's already going to be the whole list. So just as with the range, I could call on this variable that we received from the map, I can call the list function, and I get back the list. I don't need that variable, and that's what you can see in the next example, that we don't need that variable. We can just take this map and call list and get back the list of values. Now, you probably in most cases, you won't really do this because you don't really need that, but you could get back the list without this extra variable. Now, size-wise, if we look at the size of these things, you can see that, well, what can we see here? We called map on this. This is the double iterable. So this is going to be the map object. And here we call also list on the same thing, and we get back the actual list. And here you can see that the double numbers, so the list itself, once it was flattened, it's again 112 bytes. As when it was only the map object, then it was still 48. And here I could also show this table that the longer the list, the bigger the resulting, the more space the resulting list requires, and while the map object remains the same size. So that's on one thing, that the resulting map thing again saves memory. And even though this one here is a list, now, if this was originally a range, then you would save that space as well. But let's see the other thing that map actually helps us doing, or does for us. It's delaying the actual calculation. So first, what we did here, I just added a print statement in the double function. So you will be able to see when is this double function called. We have the list of values, and we call map on this, and we get back a double numbers. And then we print out these double numbers, and here is the map object. So up at this point, when this print statement is executed, so even though we called map on this one, the double function itself hasn't been executed even once. Okay, nothing happened. We just prepared the possibility of calling the double function. And then when we iterate over this map object, then we see that the double function is called, and then the value is printed. The double function is called, and the result is printed. The double function is called, and the result is printed. So each iteration will call the function when the value is needed. Now, we can go even further with this example, okay? In order to emphasize this, I created a longer list of numbers. Everything is the same. We have the double numbers printed out. So far is the same. But now what we have is that we have this extra condition to exit the loop, to break out from the loop. So we iterate over the result of the double function we iterate over this map object, but if the resulting number is greater than 42, then we stop the whole iteration. Okay, now what you can see is that we call the double function, but once we actually reach the number that breaks out the call, we stop calling the double function. So if we did it the old way, we first would iterate over all the values, call the double function on all of them, spend that energy, time, whatever that calling the double function on all the values is, and then when we iterate over the results, we break out after 4, and we actually throw away all the rest of the values, which is quite a lot of waste. Instead of that, in this way, we are actually only execute the double function for the cases that we actually needed. Okay, and the size doesn't, yeah, doesn't really matter here. It's not that interesting, the size. What was interesting really in this example is seeing that the function that was part of the map expression was only called when we started to iterate over the map object, and we stopped calling it when we don't needed it anymore. Okay, so this is what we had here. Now, everything is fine, except that, well, this is a very simple function, this double function, and in many cases, these functions that we would like to do call are rather simple, and we have a huge problem. We programmers have a huge problem is that we don't know how to give names to functions, variables, and so on. And Python nicely solved this for us. It provides what they call a lambda function or lambda expression that allows us to create functions, simple functions with a single statement only in them, but without giving them a name. So we don't have to give name to this function. The way it's done is that here I have, this is the function basically. This is the lambda function. What you can see here is that we have the lambda keyword instead of the def that we use for defining function. Then we have the list of parameters. In our case, we have a single parameter. We don't need to put them in parentheses as in the def. Let me switch back to the def for a second. So here we had the def keyword. We had the need to give the name and put the name of the variable in parentheses. In the lambda, we don't need that. We only use the lambda name and colon to separate the parameter from the actual body of the function. And we don't need to call return here because, first of all, a lambda function can only have a single expression, so you can't have multiple expressions in here. And we don't need to call return because whatever this expression is the value that is returned by this lambda function. So a lambda function is not something very fancy thing in Python. It's just an easy way. It's just a way to write a simple, very simple function without even giving it a name. So now what we have here in the map, we have a lambda function. It's just a function without a name and an iterable. And then this returns a map object on which we call the list in this case, and we got back the values. So this is for people like myself who don't know how to give names. Okay, that's sort of trying to be a joke, but the point is that sometimes when this is sort of a one-time used function or expression, then it's much easier to put it inline inside the map function than to define a function and then use its name. You have any questions? I'm just keep running here, but if you have any questions, please either stop me talking, okay, asking the question, or write in the chat so I can answer. And by the way, just I remembered, if you're watching the video, please like it, thumb up, and follow the channel. Okay, and if you're not watching the video because you're here, then please afterwards find the video and do it for me. So more people will be able to enjoy or suffer depending on your point of view while I'm explaining this. Okay, so what is this lambda in Python? This is again just a really small example. Here I created a regular function called dbl because I didn't have a better idea, returning 2 times the value it gets. Lambda can do the same for me. I can assign whatever this lambda generated into a name, and now I have a function called double. Okay, so here, look, This one doesn't execute anything. It returns the function. Anyone who is familiar with JavaScript, for example, this is basically the newer style of writing JavaScript functions. In JavaScript, you can also write in both ways, and sort of this is the much more popular way to write these days. I'm not really sure why, but that's how it is. Anyway, in Python, these functions can be really only just, the Lambda functions can only have one statement. So they are very simpler. Lambda functions, if we, let's show another example, they can also return not just a single number, they can return other things. For example, in this case, the Lambda function gets one number and returns a tuple. Of course, regular functions can do everything the tuple can do. I'm just showing that even a tuple can do this. So now if I call this double thing on number 12, what I get back is a tuple, where the first element is the original value, and the second element is the doubled value of that. It can be, it will be useful, I think, in the next example, right? So here I have a map where I'm using a lambda, okay, that returns a tuple, the tuple that we had earlier. That's why we had to see it, okay? So now we get back this map object, okay? So this pairs is a map object. You can see here the printout. This pairs is a map object. It's not the list yet. I printed it out. Now, if I iterate over the pairs, you can see that these are the tuples, okay, which are in this case also pairs. So far, fine, nothing very fancy here. We just created these tuples from the list of values. Actually, we created first the map object. There's another thing that we can do with Lambda, I mentioned. It can have more than one parameters. So in the previous one, it had only one parameter. Now it gets two parameters and then does something with the two parameters. In this case, adds them together. And this is a function now. Remember, this add is now just a regular function. Actually, at this point, we probably don't know how was that add function created, whether it was created using the def keyword or using Lambda. Maybe Python knows and you can interrogate it, but I'm not sure if we care. We can call now this function, and it's just regular add function. Again, nothing fancy. I'm just showing you that Lambda can have all these things. So map can be used now in this case to combine two iterables. And in this case, the two iterables are two lists, and I call them V1 and V2 because I'm thinking about them as vectors, okay? And don't think about them as NumPy arrays. These are just regular Python vectors, but we can do them various things with them. So if they were, let's say, NumPy arrays, or in some languages, you would think that we can do just add them together with a plus sign. But what the result is in Python is that it concatenates the two lists one after the other. So this V3, okay, that we got by adding V1 to V2 is actually the list of all the numbers. Maybe this is what you wanted, fine, then you got it. But what if you would like to add the pairwise together? So you would want to add 1 to 2, 3 to 6, 5 to 4, and 9 to 8. And create a new list of these sums. We can do this with a map and with a lambda. So here is the lambda that takes two values and adds them together, and that's it. And the map will get this as the mapping function and two iterables. And what we get back is, again, the promise of having these values. So we get back a map object, and we can iterate over it, use list to flatten it, and we get back the list of these the summed numbers. Right. this arises the question, by the way, what happens if the two lists are not the same length? And here there are I have a couple of slides because about Python 2, I'm going to skip them probably because they are not really relevant anymore. I created these slides probably about 10 years ago, I don't know, when I still have to explain the differences between Python 3 and Python 2. In Python 3, this will just stop when the shorter list stops. Okay, so this will create a list which is at the length of the shorter list. Okay, that's how Python 3 behaves. In Python 2 was funny things. Okay, so I don't need to go over that. Here I have an example which is slightly I found funny, not really that interesting maybe, but just wanted to emphasize that these two iterables, they don't have to be of the same type. They just have to be both iterables. So think we can iterate over. And in this case, the one of them is a list, the other one is a string. And here I can iterate over them. And what I do, add them together. And so when you add the string with another basically string, okay, but the other thing is an element from this one, right? So we get foo A, foo plus the A, bar plus the B, and buzz plus the C. Because here we are iterating over the elements, and here we are iterating over the individual characters. So I put here this slide because up till this point, in the examples, both vectors were the same type. Both iterables were the same type, meaning list. But you can put any iterable there, and that's what I wanted to emphasize. One of the iterables, by the way, is the file handler, and I think somewhere later on we have this example. But for now, let me see this. And actually, I'm either talking slowly, but I don't think that I talk slowly. Maybe I talk too much, but we got to already 45 minutes, and we have way too many slides ahead of us in this chapter. We'll get to that. In this example, what you can see is this is a dictionary, okay? Nothing fancy, just a plain dictionary. But what we do here is we would like to create a list of all the names from this dictionary. So all the names that mean foo, bar, and Snow White, okay? How can we do this? Well, we can, because this is, okay, so this is not a dictionary, or sorry, this is a list of dictionaries, okay? That's the right thing. So this is a list of dictionaries. So we can iterate over the individual dictionaries. So we have a lambda function that what it does, it gets back basically, it assumes to receive a dictionary, cleverly named D. I really don't like these one-letter variables, and I should update my slides, even though in really, really small functions like lambda functions, probably they are the right thing to do, because you don't want to have this drag on too long the lambda function. Sorry, I have to drink a little bit. So, right. So this one receives the dictionary and gets the name field out of it, the value of the name field. So now this would iterate over all of these dictionaries, and for each one of the dictionaries we'll access the value of the name field, and the map will build up the map object from that, and if we call list on it, it will just list all the values. We could iterate over it and so on. I had to use this a few times, this style of thing, when I needed to fetch in the like fields, specific fields from a list of dictionaries. Next slide, what's going on? Yeah, so if this was a real course, okay, I would give exercises at this point. Maybe I should give them earlier. It got a little bit long. I don't go over them now. We have the exercises, we can do solutions. You can find the slides. Feel free to try to do the exercises and then check the solutions. and then let me know how they went. Okay. Now let's use, so far we used only one tool, the map tool. Now let's see a couple of other tools. One of them is called filter. So map would map each value from iterable into some other value or some other values. Filter would actually filter out some of the values. So an original iterable that, let's say, has 10 elements, okay, if it's a list, and after the filter, we will have probably less, okay? Maybe the same number, but probably less. So here is something to filter with. There is this function, big, which would return true if the given value is bigger than 10. Not very interesting or not very complex, but can be useful. And here is a list of values. And now we can use the traditional thing, okay? So this is the traditional thing without using the filter function of Python. Just go create a new list, iterate over the elements. If the big function returns true, then append that to this list. And obviously, just to remind you, this doesn't have to be such a simple thing that requires a function. It can be a very more complex thing that requires a function. Or we could also do the same thing without a function, but this is to give you the idea and to have similar implementation. So filter looks really similar to map. It gets a function and an iterable and returns the promise again, some kind of a promise. So here we have the same beginning, and then we call filter with this big function and the numbers. And we get back something which I called big numbers. Now, if we print this out, these big numbers, you can see that this is a filter object. And we can go on with the same story that we had with map, with range, and then with map, that this has a constant size. So this has a constant size. It won't be bigger just because we have a longer list at the beginning. Okay, so that's fine. But when we iterate over the values, we get back only the big numbers. Well, bigger than 10. Same thing with lambda. We can use filter with lambda. Okay, so we don't have to define our own big function, because at the end it was really a little bit too much to define such a function for such a simple condition. We can do this. Very nice. And this one, now we are combining the two things, the filter and the map. So here we have a bunch of numbers, and we would like to double the big ones. Okay, I think that's what we want. So first we would like to filter out and have only the big numbers, and then we would like to map and double them. And you could do it on the other order, in the other way around, first map them and then do the filtering. But that would mean that you actually do the calculation also when you don't need to do the calculation, because that you would filter them out. And of course, the condition would be slightly different. So it's better that to first do the filtering, because then we have less values to work on. So what you can see here is that first I called filter, I got back the big numbers, which, as you might remember, is not the list of the big numbers. It's just the promise of being able to get the big numbers. And then we can use that promise as an iterable, as a parameter to the map, and we get back the doubles. So at this point, okay, where we reach this point, we haven't executed any of the double or big functions. And you can see it because both of them have this print statement in, so we can see it, what happens. So up till this point, nothing was executed. And then when we call the iterations, then first it calls the filtering. And because it's not a big number, it's not going through. So the next iteration calls again the filtering, and then calls again the filtering. And that's when we get to call the double as well and get back the value. So it has more iterations. The first iteration, it calls both things. It calls the filter, it calls the big function, but it doesn't get through the filter. So the next iteration is the next, and so on. So that's how we can see it. Actually, let me add something else here that no, actually I have it here. I don't need have anything. So basically what you can see is that the for loop, this print statement only comes after the first computations. But what you can also see is that we didn't call the double for these two, so we already saved that. And if we had here a condition to break out from this loop earlier, then we don't call neither the filtering nor the double for all the other values that we are when we stopped the iteration. And we didn't use any space, okay? Just these rather small objects of the filter and map objects. And of course, we don't really also need to, so back here, I called the filter, put it in here, and then called the map and put it in a new variable. We don't need that at all. We could put the whole thing in one statement. So here I'm saying for number in something that we mapped with double, and then before that it was filtered. So we are reading this from right to left, basically, taking the numbers, filtering it with big, and then mapping the filtered values with double. And that's how it works. So we don't need to have those temporary variables that we use to explain it and show that it saves space. Not that interesting. Let me skip this slide. Reduce. So this is another tool Python provides, but this is not a built-in function, not anymore. This used to be part of Python, back in Python 2. They were removed. It was removed because it's not that commonly used. I guess that's the reason. If you are familiar with the expression MapReduce or the technique of MapReduce, then these are that map and this is that reduce, basically. Okay. What reduce can do in this case, we have. Let me show you because that's probably the easiest. Here we have a list of numbers, and iterable, but this is just a list of numbers, and this is the lambda expression. So the lambda expression gets. For reduce, we have to get it has to get two values and returning one value. And what the lambda expression does, it takes the first two values, calls what the reduce does, sorry, calls the first two values, calls the function, okay, this function, okay, calls the function on it, gets the result, and then calls the function on the result and the third value. Then gets the result and calls the function on the result and the fourth value, and so on until it goes through all the values. So because we did it plus plus, it's basically summing the numbers. Okay, so that's why it's not. I don't really have very interesting examples with this. Only examples that they have really more or less functions for them, like sum. Okay, so you don't really need the implement it yourself. You can, well, actually this one, I don't think that we have a multiple all these numbers, but this one is very similar. It just multiplies all the values. Okay, it's basically putting a multiplication between every two of them. Okay, here I put here a mathematical expression with all the parentheses. Okay, that actually happens here. So this would multiply all the values. We can divide all the values, but of course you have to be careful what's going on, division by zero and so on, not to deal with problems. You can have it what if you have one list, okay, one element list, so it's fine. It's fine. The problem, there is a slight problem when the list is empty. So here we have a list which is empty, and I call it and it says reduce of empty sequence with no initial value. which actually hints of how to solve this problem, okay, because this is an error. The way to solve it is that we can provide an additional parameter to the reduce function, which is the initial value. So it pretends as if there was this value before the whole iterable. Okay, and that's how you can solve the problem of empty lists passed to reduce. Okay, you can do we do some reduce here on a list of dictionaries, basically summing up the grades. I guess that's what I'm doing here. Zip. Okay, that's a fun thing. Again, here we have actually three lists. The details of the members of the Monty Python troupe. And we call the zip function on the iterables, and it returns us basically a tuple of, in this case, 3 elements, one from each of the iterables, and in this case, one from each list. And then we can do whatever we like with that. So this allows us to combine these these things. Basically, I think we can do quite similar things with map as well, but zip can help you sometimes. Okay, not that interesting anymore. Okay, so here I use this to create a dictionary, and this happened to me a few times that I needed this. I have basically the keys that will be the keys. Okay, so I have 2 lists. One of them will become, one of the values of one of them will become the keys of a dictionary, and the other values are the values from the other one are to become the values of that dictionary. I can use the zip to combine the 2 into a zipped list. This is basically tuples, and then we can use the dict function to convert a list of tuples into a dictionary. Let me change this a little bit. Create dict using zip. This is it called. Creating dict using zip by. Let me print out the zipped thing. Let's see if this works. Yeah, okay. So here you can see that what we get back is a zip object, not a list. And now we will have a problem showing the next one. So what if I call list on it? Okay, so you can see that this is basically what the zipped returned or would have returned. Okay, the zip returned the object, the zipped object, and you're welcome, those people who need to go, fine. I promised 1 hour, and 1 hour is done, so we're going to finish soon, but if someone has to go, fine, and you're welcome. So this is the zip object, the promise of going over the things. This is the list of tuples, and you might be surprised, or maybe not, that now the dictionary is empty. Why is the dictionary empty? Because when we call it list, it actually consumed all that zip object. So it's done now. So in order to have the dictionary, I have to regenerate this zipped thing again. And now if I call it, now I have the dictionary. Okay, so you have to remember that these things, they don't hold the data. They will calculate for you on the fly, but if you did it once, then it's gone. Okay, they won't calculate it again. You have to initiate this calculation again if you would like to do that. Okay, so there are other tools like all and any that all would return true if all of the elements, okay, that's the right, if all of the elements are true, and any would return true if any of the elements is true. Okay, and would false if everything is false, and here would be false if even one is false. Okay, this is another thing. People who use NumPy or NumPy, pandas, I don't know, whatever, but yeah, they can already do such things in the language. Wait a second, sorry, stop it. This is what I wanted to show. You can just compare 2 with 1, fine, you get true, 0 is false. So just comparing numbers is fine. But what if I would like to compare the numbers list with a single value? So something like this. Okay, let me show you. Can we do it? Can't do it in pure Python because Python can't compare, Python 3 can't compare 2 different types of values, lists with scalar values, with int in this case. And NumPy can do this, but we don't deal with NumPy here. So how can we do this in pure Python? We can use the map function, okay, to go over all the numbers, and for each one of them, do the comparison. This will return us a map object. And we can use all on that to check whether all of them are true or all of them are false, or if all of them are true or some of them are false. And the same way we can do another condition here. So we can combine the map and then the all or the any of these tools. Okay, a little bit more and then we are done, I think. Let me actually check it. Okay, wrong key. I forgot the keyboard. Yeah, so we are quite close. Where are we? All and any. Well, 43 out of there are exercises here. So we are getting close. Okay, and I'm going to finish it. But let's finish this chapter now. So some of you might know the list comprehension, so the syntax which we call list comprehension. And actually many Python programmers say that they prefer list comprehension to map, but they basically do the same, well, except the list comprehension is not lazy, which is a bad thing that it's not lazy. So here what we have is, again, the double thing. We have the list of numbers, and then we have this expression, which is in square brackets. We say, call the double n for every n in the numbers list. So these numbers can be n-iterable in this case, okay? Just like with the map function. In this case, this is a list, but it can be n-iterable. And what we get back is the list of the computed values. But it's the list. It's already a list. So this one already does all the computation just by executing this expression, unlike the map that only did the computation when we actually needed the values. Okay, same, this is not very interesting. The other one, this is the interesting one. The other one does the same. So this is what we call list comprehension. Same idea basically as map, but it's what we call eager. So it will immediately, or it will do the calculations as soon as possible. Unlike the map and filter and other functions that we saw that are lazy, so they will only execute it when it really, really needed. And in this case, too, laziness is good because it saves us CPU at the beginning, or computation, CPU time, and so on. Okay, this is let's not go in deeper in this one. Less interesting. Actually, I think what I'm showing here is I'm showing here that the map does this, and then it saves space because it only takes up 56. while the other one creates the whole list and it takes more. You already know this. I don't have to go. There is something else which is usually called generator expression. When you have the same thing as we had earlier with the list comprehension, but in this case we put parentheses around it. So instead of square brackets, instead of, let me go back, instead of the square brackets, we have the same expression inside, but we have parentheses there. This will create a generator here. And you can see if we call this, we have this expression assigned to something and print it out, what we get back is a generator object. So this one doesn't do the computation upfront. It only creates the possibility of doing the calculation. It's slightly bigger, I guess. It takes some more whatever in the Python construct. Actually, it's also possible that these numbers will be different depending on the version of Python, because this is just some implementation detail. But they are some fixed size given in the same Python, and it might be also platform dependent. I have no idea. The point is that this is a relatively small number and fixed, unrelated to the size of the iterable that we go over. And then we can iterate over just like as we did earlier and get the values. Okay, so if you used list comprehension earlier with the square brackets, you can replace them with parentheses, and then well, it might change the behavior of your code. So remember that it's not just like you can freely replace it, because you might rely on the fact that the values were calculated upfront. But this can be useful because it won't do all the calculation upfront. It will just create you, again, the promise of having those calculations. And just more example is list comprehension. Here we're using the same thing with dictionaries. Yeah, so this is a dict comprehension, okay, where we have a curly braces around it, and it generates at the end, it creates a dictionary. This lookup table is not that interesting. I think we are, well, there's one more example that I know that the example in the slides is actually not good, and I fixed it earlier, and I mean returned it to this one because I wanted to show you this one. So here we get the name of a file from the command line file. We open the file for reading, and then we call this map, which what it does, it removes the trailing new line from each line. So what it gets the FH read lines, okay? The FH read lines will read in all the lines from the file, and then this is an iterable, right? And we iterate over and use the map, and we get back the rows, which, as you know, it's a promise. So it's not doing the R strip. And then we can print out the lines. So let's just read lines without new lines. This is the code. Python read lines without the new lines. And I can provide it, let's say, what was the previous one? Create dict using zip, just some file. And what it does, it just prints out the lines. So it's not very attractive what we can see here. It just reads in it's like cat, okay? It reads in on the lines, it removes the new line from the end, and then it prints the line out, and the print automatically adds the new line, so you just see the content of the file. But the point was here is that we can use this lambda on something iterable. What I missed in this example, and maybe let me see that, yeah, I don't explain it. What I missed is that when I wrote it, that this FH read lines actually already reads all the lines into memory. So what we have here is that we have all the lines already in the memory after executing this expression. But we could do better, because FH itself is an iterable. So you know that we can write for row in FH. Let me edit this file and then I show you. right? So we could write something like this: for row in FH, blah, blah, blah. Okay, so you can see that this is an iterable, the FH. This is quite common way to write, iterate over rows. And in this case, if I write it this way, something, then in each iteration, it will read in a new line. So it's way less wasteful because you don't need read the whole file into memory. And in this case, I did read all the lines into memory. I could replace it, and I put it in comment out, so we'll have it here. I can actually put here just the FH because it's an iterable. So now the lambda will, the map will create this promise of I will read the lines from the file and then strip the new line if you really want it. Now, so this one, in this case, we don't read in the file up front. We only read the file when we are actually, we only read the next row when we would like to access the next row. But this solution is broken now. Let's look at it for a couple of seconds, and then I'll run it and try to figure out what's the problem. I didn't think about the problem when I edited the file earlier. So let me run this. And this is what I get back. Value error IO operation on closed file. Why? Because we have this with statement, and earlier we read from the file inside the with statement. Now, because we just take this file handler and pass it into this, it's embedded somehow in this map object, but we start calling the file handler only here. But the whole idea of this with thing is that when we leave the block, the indented part of the with thing, then it automatically calls close on the file handler. So we don't have the file open anymore at this point. In order to fix this, I need to indent these rows so they will be part of the with statement. And now it works. Okay? And this one, this saves a lot of memory because it doesn't read the whole file into memory. It just reads row by row, and for every row, it does the rstrip thing and then prints it out. Okay, so this is the way better solution than what we have in the slide. And I think that's it. There are a couple of other things here, but they're not that important. And I already passed an hour and 50 minutes, so way too much. So thank you for being here. As I mentioned at the beginning, I'm going to stop now the video. And then if you stay around, feel free to ask questions, or we can discuss anything you like about Python or finding jobs, or I don't know, whatever, or what kind of presentations you would like to have in one of the upcoming meetings. So feel free to do that. If you're watching the video, thank you for watching the video. Please remember to thumbs up and follow the channel, and support me through one of those support channels so I can do this a lot more. Okay, so thank you very much and see you next time.